welcome everybody to our program here at about Cobra project. I'm Ashraf Labib, professor at the University of Portsmouth, and it's my pleasure to welcome Professor Jeremy Howells, our dean, and he's also the pro-vice chancellor for research, innovation, and external relations. This would be followed by an introduction by Professor Rushdie Marzouki, who is the coordinator of the project, and then Ms. Sarah Wilby will give us an overall introduction about the project and from the clinical perspective. We will then followed by real-time calculation by myself and the real-time radiation by Dr. Kevin Brown from Oscar Lambert, and the biopsy module from DEMCON by Mr. Peter Whisker. Then we have a presentation from Delft University about the needle design, and this would be in the form of a video. And the most important, I think, is the demonstration of the robotic solution. This was supposed to be done here in Portsmouth, but due to problems with risk and transferring the robot from France to here, this was not possible. So we will do this in real time online from University of Lille. So over to Professor Jeremy Howells, and thank you very much for coming.
Thank you very much, Ashraf. So I'm really pleased to welcome everybody. It's unfortunate you can't be here in person, but you seem to have a really jam-packed day of discussions and presentations. So I really hope it goes well. I'm really pleased that Portsmouth Business School and the School of Mathematics here at Portsmouth are involved with the project, together with academics and clinicians from Portsmouth Hospital University Trust, in this really important area of cancer research, particularly focused on prostate cancer. I would also, in particular, like to welcome those design experts from the University of Lille, who are the lead partners in this project. I'm sorry you couldn't manage to bring your kit over, but hopefully you will be able to do that at some stage. I'd also like to welcome participants from the University of Delft, where you're working on this non-ferrous needle, which is so important with use for MRI. And then coming back to Portsmouth itself, the medics and clinicians from Queen Alexandra Hospital here in Portsmouth as well. Well, I'm really talking to those who already know, but obviously you're nearing the end of this project, this 3.3 million euro project. Having been involved in European projects, you're always worried about the actual outcomes, but it looks from the work you've done is really key. You've got some really important findings. You've made incredible progress. So I think, you deserve real praise and support. And certainly here from Portsmouth, we will provide as much ongoing support as possible once the project ends shortly in September. I understand you've got another, the main conference event in June, so I hope that goes well in Lille. So I hope everybody can attend that. Probably they will if the robotics is there. And obviously, last but not least, prostate cancer is such, 1.4 million cases, second most frequent cancer in males, and over 350,000 cases of death per year. So it's a really important topic. You've made incredible progress. I know because I've seen another presentation earlier this week, and I hope you have a really successful time today. So thank you very much. I hope cockpit, the final landing stages like a plane of the project goes well. And as I say, Portsmouth will provide as much support it can in these final stages. So thank you.
Thank you very much.
Back to you, Ashraf.
Thank you very much, Professor Howes. And if your time permits at any time to join in, please do so at your leisure. Thank you very much for your
Okay,
thank you very much. Thank you.
Bye.
Thank you. Bye-bye. Okay, thank you very much. And now I think we are a bit earlier than the schedule, but I can see people are joining as well. And we have Ms. Sarah Wilby. Sorry, the introduction by Professor Rojdi Marzuki. Did Rojdi join us? I cannot see him in the attendees. Rojdi.
We can switch it around if you want, Ashraf. I don't mind doing mine first if maybe Rojdi's having issues joining or something.
I would say so, yeah. If that's and if Maximilian can kindly contact Rojdi, please, that will be fine. And Sarah can take over now. Yeah. Okay.
Okay, I'll just share my screen. Yes,
please do so. Can you share your screen?
I think I need you to stop sharing yours first of all, and then.
Yes, let me do that. Yeah. You are.
Okay. Right. Okay, can you see my slides?
Yes.
Yep. Okay. So first of all, apologies that I'm having to stand in on behalf of our urologist. We should have had a urologist talking today, but unfortunately he has COVID, so that is still an ongoing issue. So I will give this instead. So yes, I'm presenting on behalf of all the Cobra collaborators, just to give you a little bit of an introduction to the project and clinical perspective. So I work myself as a clinical scientist in radiotherapy, and I've been involved in the project throughout. I'm working also with the University of Portsmouth on my PhD related to this project. So the project began on the 1st of January in 2018, and as has already been stated, it's coming to an end September in this year. So it's an EU-funded project across the two seas region, which you can see in the green there on the diagram. And so the project aim is to improve the quality of both diagnosis and treatment of localized cancers by developing a new medical robot prototype for use in MRI. And we'll come on to the details of that shortly. So we have a number of partners working with us, as you can see here, and they will each be introduced and take their part in the workshop. So Cobra, in the first instance, is focusing on prostate cancer, addressing both the diagnostic and the therapeutic aspects. So both of these procedures offer the opportunity to replace the manual needle insertion procedure with a robotic technique. And we'll just briefly discuss the potential benefits of this. Before discussing the potential benefits of this, I'll just give you a few statistics about why prostate. We already had some of this previously from Jeremy Howell, but in 2020, the worldwide statistics showed us that there were 1.4 million new cases of prostate cancer. It's the second most frequent cancer in males, leads to 375,000 deaths worldwide, and it's the fifth leading cause of cancer mortality. So in terms of our current practice, focusing first of all on biopsy. Prostate biopsies always used to be performed transrectally, and that's still the case in some centres, but there's been a big shift towards transperineal biopsies, and in our trust, 100% of our biopsies are performed through the transperineal approach. But across the board, there's quite a variety in how this technique is performed. It's an ever-changing field. Some of them are template guided, some of them are freehand, some centres use general anaesthetic, some use local anaesthetic. So there's quite a bit of variety between all the centres. So the graph at the bottom centre here shows the change in the number of transperineal biopsies being performed by NHS trusts, and this was between 2014 and 2017. So we can see a huge increase in the number of transperineal procedures. And in 2019, there was a national prostate cancer audit, and the graph on the right shows the results of this. So one of the major benefits of doing the procedure through the transperineal approach is to reduce the amount of sepsis, and that's the dark blue bar here in this chart. And so we can see that sepsis has been reduced. But similarly, there's a large increase in the amount of urinary retention, which is in the dark red here. And the reason for that is likely to be due to the number of samples taken, because with the transperineal approach, you tend to take a much higher number of samples than transrectal. And the only way to reduce this is to be really confident about where we're hitting. So being really sure that we're hitting the lesion, if we have that confidence, then we can reduce the number of samples that we take. And so for that, imaging is really, really crucial. So in our trust, we've already moved from an ultrasound only approach to using ultrasound and MRI image registration. And we use multi-parametric MRI for our diagnostic technique, and then we fuse with the ultrasound in theatre to guide the urologists in sampling the biopsy. And we get much more information from this multiparametric MRI approach than we would from ultrasound alone. And the workflow at the bottom here just shows the fusion process of the MRI with the ultrasound. So the brachytherapy process is very similar setup, transperineal, and similarly having to use the needles. And whether or not that's permanent with low dose rate or temporary high dose rate brachytherapy, the approach is much the same. And we're having to consider sparing the organs at risk, so the urethra, bladder, rectum, seminal vesicles, whilst covering the prostate itself. And there's a move towards also boosting the dose to the lesions, and we now have that information from the MRI. So I'm sure some centres are already doing MRI-guided prostate brachytherapy or fusing the two. So whichever technique you're looking at, whether it's biopsy or brachytherapy, there is a need for precision. So in biopsy, the lesions may be as small as just half a cc in diameter, and they can be hidden in a prostate volume that's up to 120 cc. So difficult to target that unless you've got good imaging. In brachytherapy, you have the steep dose gradients around the source. You have anatomically close organs at risk, and the risk of seed migration if loose seeds are delivered outside of the prostate capsule. So precision is important for these techniques. So in terms of the limitations of the current practice, we have insufficient information if we use ultrasound alone. We can't see the lesions on the ultrasound, we can just see the border of the prostate. We can fuse them, that is an option, but there's a risk of misalignment if using both ultrasound and MRI. And also it's difficult to track the deformations of the prostate during the procedure. It can shift, it can deform, and trying to keep up with the fusion of the ultrasound and the MRI during that process can be difficult. Straight needles and templates limit our access to parts of the prostate gland. We can get obstructions which can be caused by the pubic arch, by the angle of the urethra, calcifications. And furthermore, there's inter-operator variability, and that's the case with both biopsies and brachytherapy. So by introducing some form of automation, we can hopefully smooth out some of the interoperator variability that we see here. So the Cobra project aims to address these limitations, and the linchpin for this is the robotic arm, which is being designed by the University of Lille. But it doesn't work on its own. There are a number of modules associated with the robotic arm to cover these different issues. So firstly, there's an automatic seed loader for the delivery of the iodine 125 seeds. There's a biopsy module that attaches to the robot to acquire the biopsy samples. There's steerable needle, which enables us to work around some of the obstructions that we see, such as the pubic arch. There's a planning for this trajectory path of the steerable needle and the seed positions. There's software devised to calculate the dose on MRI using pseudo CTs, and the development of a bio-inspired phantom for the testing and training of the system. And of course, key to this is that all of these are MRI compatible and work directly within the bore of the robot. And that differs to some of the other robotic systems that are out there, where the patient has to be taken outside of the MR scanner. The couch has to be withdrawn slightly for the procedure to take place, and then they can go back into the bore itself for the imaging. This is designed to be fully compatible in the MRI bore. So in terms of the program, I think we have up next discussions on the trajectory calculation, which was from the University of Portsmouth, and then the radiation dose calculation from Centre Oscar Lambert. DEMCOM will talk about the biopsy module. TU Delft will give us an introduction to the steerable needle, and the University of Lille will then give us a full live demonstration of the integrated robot. So I hope that's okay as an introduction, and enjoy the workshop.
Thank you very much, Sarah. Thank you very much. And also thank you for stepping in at such short notice.
Okay.
Now that we have Professor Rujdi Marzouki with us, I pass over to Professor Rujdi Marzouki, who is the coordinator of the whole project, of the whole Cobra project from University of Lille. And if Rujdi wishes to share.
Good morning, everyone. Thank you, Ashraf, for your introduction. Thank you, Sarah, for the brief description of the Cobra project. I want just through this a few-minute presentation of on the context of the Cobra project and why collaborative Interreg 2C program contributed this last period in this challenge development. So the Cobra project is co-funded by a European program called Interreg 2Cs that is targeted here with the green colors. It regroups different regions from these 2Cs from France, north of France, west of Belgium, west of the Netherlands, and the south of UK. So the common challenge of Cobra project concern the cancer control plan, where the partners of Cobra were interested in technological innovation related to minimally invasive technology for intervention in local targeted for diagnosis and treatment of cancers. So the main objective of Cobra project was to improve of quality of diagnosis and treatment of localized prostate organ cancer using robotized technology which can operate inside MR environment. Here, yeah, our main interest in terms of technological innovation is that this technology can operate fully inside AMAR. So the partnership of Cobra is divided in 4 classes, coming from academic partners. We have here University of Leeds, which lead this project, University or Technological University of Delft, University of Portsmouth. We have also medical partners, which are Oncovet Clinical Research, which is a research center for veterinary applications for in oncology. Centre Oscar Lambry, which is oncological hospital here in north of France, and NHS Portsmouth Hospital. We have a cluster of medical sector, which is Eurasante, which co-manage the preparation of this workshop, and 2 industrial or private companies, Satnor, in charge of the industrialization and patenting of the project results, and Denkamp from Netherlands, in charge of biopsy module development. Also, the ecosystem of Cobra project has been enriched with the participation of multiple observers from Europe and outside Europe that are listed here as medical partners and industrial partners. To make a positioning about the technology that we collaboratively contribute in this Cobra project, from radiation therapy versus MRI, existing technology has been developed for external radiation therapy, like the AMAR LINAC, even from the cooperation, the jointly cooperation between Electa and Philips, or ViewRay, which has widely presented this during the last ISRO event. So this technology is focused on external radiation therapy coupled with AMAR, that we can adaptively track the targets online, one of the advantage also. And what we want to converge during through Cobra project is to focus on local radiation therapy in terms of brachytherapy, but under AMAR. This is what we planned to develop during this 4 years of project life. So here, in terms of integrated design, the Cobra project started from TRL 0, which concerns the requirement and specifications coming from the medical staff, principally how we can use, what are the advantages of using robotized technology for making a local intervention or minimally invasive intervention for diagnosis or treatment of cancers for the prostate. One of these advantages is, let's say that in the era of 2022, the attractivity of digitalization is for medical staff, even if new resident, is more and more in progress. So how this technology can facilitate the applicativity of the intervention and with by improving the quality of the treatment with the assistance of this robot. So this has been listed during the requirement in 2018. And after that, the specification in terms of accuracy, in terms of repeatability, in terms of image data driving has been identified with a compromise manner to build the other TLLs, to start in the system design in collaborative way. What means collaborative way? That means we have multi-partners here. Every partner is specialized in one task, and the aim after how we can integrate all the solutions produced by these multiple partners in multiple fields in one main output or main delivery. For that, we have to respect the same structure. And actually, the version that we can see here on this figure of this robot is reaching a TRL 5 in a frame of 8, and we are expecting to reach the TRL 6 by finalizing the trials on live animals during June 2022. Here is the overview of our robot intervention lab in AMR conditions, where we can see the patient placed in lithotomy position and the robot operating in a specific workspace, allowing the operator to teleoperate it in semi-autonomous conditions or in full conditions. And this is what we will see during the coming demonstration online. Thank you. And I finished this introduction, and I let the colleagues.
Thank you very much, Professor Marzouki. And I will just go back again to the agenda just to share it, and then we we are back to the agenda. We are a bit ahead of time, so we'll see if we can maybe take some time like a short break. But I will start with my presentation if that's okay, and then we can perhaps go for a break afterwards to be in line with the time. And as Professor Marzouki has mentioned, he spoke about the robot, but hopefully today we will look also. It's in the plan of today is to have a full demonstration of the robotic system in real time from University of Lille as well, to demonstrate what Professor Marzouki have just mentioned now. Okay, so I will start by looking at sorry, it's not working. For some reason, I cannot get my screen to work. Oh yes, okay, I'm sharing the wrong screen. Let me share the right screen. Can you see my screen?
We can see like a slide deck.
Can you see it now?
We can see the presenter notes bit of it rather than the main. I think you're still showing the wrong screen.
Yeah, okay. I have. Can you see my screen? Presentation? Okay, let me so can you see my presentation now? No?
We can see the presenter notes part
Okay.
of it. So, I mean, we can see your slides.
Okay.
We can also see your notes. Might not matter.
Okay. Let me no. Let me try another last time, and then if it's not, I will continue this motion. Yes. Okay. I'm sharing the wrong screen. Yeah, I can see where I'm going wrong. Should be this one. Okay. Should be now fine. Yes.
Yes, that's good.
Okay, that's good. So it's about the real-time calculation of the steerable needle for the optimized brachytherapy, and apologies for the delay. The role of the, as Professor Merzuki and Sarah has mentioned before, that this is an overall like flow chart of the different partners and what each of them is contributing. Our role really is to focus on the trajectory planning, which is this bit here at the top of the screen. This would have an input coming from the calculations, and the output goes to the software interface, to the robot guide, which will then go to the either to do the biopsy module or the LDR or HDR, what we're focusing on the LDR. LDR is the low dose radiation module. So it can do, as I said, both biopsy and LDR. So the main, this talk, I'm going to focus on the formulation and data structure used for the path planning and the real-time path adaptation program, as well as an automated algorithm for the needle trajectory planning in the context of robot brachytherapy and biopsy. So in terms of the two main criteria, we have to achieve an adequate dose distribution as closely as possible, but at the same time, we have to minimize the number of needle insertions. So we are optimizing the path of the needle of that route. In this work, it has been assumed that the seed plan has already been prepared and fed to the trajectory planning algorithm using the conventional seed planning methods. Also, it has been assumed that the orientation of the seeds can change with respect to the original plan without violating the radiation field requirements. I will go back to this latest assumption about the reorientation because it's really vital in our case because of the design of the needle itself. So the main challenges here is that we want to avoid the organs at risk, like the urethra and the bladder, the uncertainty due to the organ moving, and the radiation field from seeds is dependent on its alignment. So we developed like an integrated approach based on C++ that have the MRI feedback simulated into real-time module, and we have the robot controller that would lead to the robot inventor, which is simulated by the University of Yale. So the main innovation here, as well, one of the main innovations is that the needle, the algorithm is made for a needle design developed by University of Delft in the Netherlands, and they are going to present about the design in more detail later on, comprising of straight rigid cannula and a pre-bent stylus that keeps it intended curvature once deployed inside the patient's body. So the algorithm assumes a circular curvature for this stylus. And this circular curvature give us or give the robot more flexibility so that we can reach areas or avoid areas which needs to be avoided. So we know from this operation that one of the most important part of the success of this operation is to avoid the neurovascular bundles. Otherwise, the patients might have side effects and so on. So the advantage of having this circular of curvature is to do exactly that. So the algorithm is required to minimize the patient trauma by minimizing the needle movements and the number of insertion using oblique insertions. And the seed usually is placed at the accuracy of 1 millimeter. Usually you would have because we are assuming that this is coming to the seed plan is coming, assuming that it is a straight needle. Usually you will have coordinates of two types of information, the X and Y, as well as the number of seeds for every needle that go through this grid, which Sarah has shared with you earlier on. The result of what we have developed is that we can actually do this sort of calculation in between 6 to 9 seconds to plan the trajectory. But the main limitation is that we are assuming here that it's straight needles because the plan is coming as a straight needle. But we then generate different scenarios, and instead of having straight needles going through the prostate, we would have one needle through the robot, which is curvature, but it generates the same, or try to reach the same amount of targets as the straight needles would do, the multiple straight needles would do. And this is really one of the main objectives of this project, is to minimize the insertions of number of needles as well. So we developed like a contour for the finite element analysis, and we also simulated the organs at risk, like the urethra, and the path of the needle itself. As you can see here, so how and to avoid and to measure the distance with the urethra. And one of the most important assumptions to be noted here, as I mentioned before, is that the plan is that the needles or the generation of the orientation of the seeds, if they change, they will not affect the radiation of the dose radiation calculation. So whether the seeds, just to let you know, is the size of it is like the size of a piece of rice. So if it is reoriented in a different direction, because it's not a straight needle, this will not affect the total radiation of the whole volume of the prostate. This is one of the KPIs, or the key performance indicators of how much radiation did we cover through the insertion of the needle of the seeds by the needles. The system would generate the curvatures, the different curvatures, and based on the calculations, it will decide where to place the seeds. We had obviously to have some sort of weighting factors, because our algorithm assign weights to different criteria. This is a very classical multiple criteria decision-making method. So we are looking, for example, at a weight, and we got this weights from discussion with urologists from Queen Alexandra Hospital. So, for example, how much weight should we give to the tissue damage inside the prostate versus the tissue damage outside the prostate, for example, just to give you an idea about the weighting mechanism which goes into this algorithm. And then we also want to, so taking into consideration the minimization of the weight tissue damage, we generate the different scenarios, and we choose the scenario for the robot or for the needle path that would achieve as many of this objective as possible. And you can see here, then it would say, okay, put this needle, and obviously it generates different forms, and the new algorithm, the act of penetrating the prostate causes movement and deformation, after which the correction mechanism is required. The stylet should be pushed out when the cannula is inside the prostate to maintain the correction mechanism, but we cannot pull the needle out. So this is again one of the constraints, because medically, once you pull the needle out of the patient, you have to change the needle. You cannot insert the same needle again. So to avoid that, we keep the needle inside the patient, but outside of the prostate if we can. So the traditional one has a straight needle, whereas in our case there is an angle to the insertion itself. And here is the trajectory algorithm that has been developed by our team. And you can see the prostate in blue color, in light blue color, and the organs at risk in yellowish color, and then the different scenarios that are generated by the model. And this is another view of the different scenarios that the system would generate. So this software has been designed in such a way to be user-friendly. So this is the user interface of the software, which shows the different parameters or the different weights, for example, that can be assigned to different aspects of the for the calculations. And just to show you the idea of suboptimality or the trade-offs that being done, for example, here we have both plans, seed plans, we are reaching the same acceptable radiation field. Whereas in seed plan A, we have an optimal trajectory. In plan B or second plan 2, we have suboptimal trajectory. Whereas the advantage of plan A is we have single insertion over multiple insertions in plan 2. So as you can see here, you are always trading off between different factors when you are doing such methodology. And this is really the problem which we are trying to address, is how do we give which weights, different weights to different criteria, and we try to find the optimum solution based on that. So the potential advantage of the Cobra project through this method is that the neurovascular bundles would be hopefully saved or not damaged. As we know from the current statistics, 50% of patients suffer from ED, erectile dysfunction. And also the other advantage is that usually this operation is limited to the size of the prostate. So if it's a large size, like more than 50 centimeters cube volume, it will not qualify to do brachytherapy in the first place. Whereas with our method that we have this curvature, which gives sort of flexibility, and we can reach different areas and so on, we can extend the number of patients who would be qualified to do this more accurate or more precise method, which is a treatment, which is the brachytherapy treatment. So as a conclusion, the fundamental limitation of this method, which is caused by the fact that the seed planning has been done separately from the trajectory planning. This is the main advantage, which we think in the future follow-up on this project, we should combine both the seed planning and the trajectory planning. And also, the problem here is that in conventional planning, we have stranded seeds, whereas in our method, the main limitation that we cannot use stranded seeds because of the curvature in the needle. So to avoid migration of the seeds outside the prostate. Nevertheless, in terms of biopsy, we satisfy all the requirements. So in terms of LDR, we are still lacking behind because of this lack of stranded planning seeds. But in terms of biopsy, we satisfy all the requirements. So it is envisioned that experiments will validate the proposed approach, as Professor Marzouki was mentioning, that this will be tested on dogs in the future. and that future research can be done to explore the use of machine learning, deep learning, to optimize the weights of these different criteria. Thank you very much. And sorry for the initial delay, but we still have time. So I think with respect to time, we are fine. Maximilian, do you suggest we continue on the program?
At this point, do we have some questions from the audience?
I will stop sharing. Any questions? Okay, let me go back to the program. We have real-time radiation dose calculation. So if Kevin is around, we can start, or
yes, I am. Yes.
Or if you want, we take a break, whichever you. Kevin is around? Okay, yeah, okay.
Yeah.
So shall we continue then? Okay. So
I will share my screen.
yes,
Yeah.
please, yes, Kevin.
Okay. Thank you. See it. Perfect. So I'm Kevin Bouboni, and I've been working during my PhD at the Centre Oscar Lombre. And the goal of the Cobra project is to build a brachytherapy device under MRI guidance. This implies numerous challenges, and during my PhD, we were working on two aspects. On one hand, a solution robust to MR intensity variability, since every MRI acquisition can be different according to the machine, constructor, sequence, and acquisition parameter. On the second hand, the use of this device in real time. Since its introduction in the late 70s until now, MRI is more and more used in radiation therapy. It is particularly appreciated for a superior soft tissue contrast compared to with CT. As a result, MRI helps to better discern tumor than CT, and have therefore been integrated into radiation therapy practice and as a diagnostic images. Tumor volume is delineated more precisely on MRI compared with CT. The ideal treatment workflow with MRI guided radiation therapy is first the MRI simulation to acquire the 3D geometry of the patient, then the contouring of organ trace and the target by the radiation therapist. Three, the dosimetry. Basically, a treatment plan is created according to the prescription. And finally, the treatment delivery. A problem occurs at point 3 since the treatment plan is created from a CT because it gives necessary information to compute the photon interaction in the medium. So basically, those calculations cannot be performed directly on MR image since there is no correlation between MR intensity and electron density. And due to the real-time computation, to make this possible, we oriented ourselves with deep learning, and in terms of image generation, generative adversarial network, a kind of deep learning family, work extremely well. So we investigate two methods. The first one is when we have basically to use deep learning, we need a data set. So to make the correlation between an MRI image and a CT, we need a numerous pair of image of CT and MRI. But basically, on the left, when we have pair image is when there is a non-rigid registration between the CT and the MRI. When we are in this case, we basically need to use a conditional GAN. We will explain it later. And when do we not have paired data, it's called unpaired data. And in this case, these images are just religiously registered and we can use different kind of patient to make it possible. The basic scheme of this study is first a pre-processing of this image. Oh, on the left. So basically, we just remove the table from the CT, the MRI, and then the learning phase, in which we make it learn by our generative adversarial net, and then a synthesis. To evaluate our result, we then use our trained model to evaluate it on patient not seen in training, and then we perform a treatment plan from the real CT and also on the synthetic CT, and we compare the dose in order to evaluate the performance of our model. The major contribution of the first study is the improvement of the generalization issue in deep learning. So far, no one have been able to generate a synthetic CT with multi-center data, and that is because first, usually people don't need to use multi-center data because they work in one center with one MRI, and basically there is no reason to use multi-center data. But due to the Cobra project, we do not have the MRI sequence dedicated to our project. So to make it possible and to be in advance, we decide to use different kinds of MRI and CT to be able to, at the final point, when we will need to evaluate our model with the new Cobra MRI, it will be possible to have good results without needed to retrain a network. So basically, this study has been published 2 years ago, and it was the first appearance of a multi-center data with the SCT. So basically, we use a training power patch, and the synthesis took only less than 10 seconds, considering that we have been using 100 slides. So basically, it can be considered at real time. The dataset has been taken from the God Atlas project. So basically, there is just 3 different sites. We use the first and the second one for training, and the third one to test. In terms of those differences, as you can say, basically there is, well, I will not say there is none, but as you can see, the main dose difference appear in higher dose regions. Basically, this is a prostate treatment, and mean relative dose difference to the prescription is under 1%. So basically, it's clinically acceptable. Further, we have been gone to unsupervised generalization. It's a more complex model. That's why we have not been able to use the fully size of the images. But still, quite recently, a paper about the second configuration has been published with more data and variability in testing while being more simple to train, since there is no need to elastic deformation. As you can see, we increase the number of patients. In this time, the training use 3 different sites, and we test it on patients from the Centre Oscar Lambré this time and Institut Jules Bordet, where I've been working now. In terms of those difference, as you can see, there is a lot of difference at the border of the patient. This is basically due to the use of only registration. But as you can expect, the goal is not to, we are not focused on the border of the patient, but mainly inside where the target is placed. And in this case, the mean relative dose difference to the prescription in either registration is also under 1%, so clinically available. But even if we obtain the electron density, compute an accurate dose distribution in matter of seconds is quite impossible. Accurate dose calculation can be achieved with model-based calculation algorithm with Monte Carlo method being the gold standard. But Monte Carlo method use computed tomography to assign voxel by voxel tissue mass density and elemental composition to calculate those two medium. Similar information is also provided for the Similar information is also provided for the radiation source and applicator. However, traditional central processing unit-based Monte Carlo calculations are not optimal for clinical application in real time because of the slow computational speed. Accuracy of the absorbed dose calculated with the Monte Carlo method ties closely with the number of primary particles involved in the simulation. That's why, once again, we are looking for a deep learning solution to predict a Monte Carlo dose distribution. First, I would say we need a computer tomography. That's why we have been converting the MRI into a synthetic CT. Then we need to know exactly the input. Second, the treatment plan in which we extract the 3D position of the source into a 3D matrix called here soft treatment plan. And finally, we assign these two volumes. We align these two volumes for ease of use. Basically, it's just a result registration. Even if this time we do not need a particular type of deep learning solution, we have been using a CNN called film generator. And even if deep learning for inference is fast, 3D is still a challenge. That's why we encode the synthetic CT with a feature-wise linear anti-modulation. It allows to condition information by extracting in the SCT only important feature needed to translate the soft treatment plan into a dose distribution. Since we do not have sufficient Monte Carlo data for training, therefore we replace it with those computed on the treatment planning system. This step is known as transfer learning. We do not perform quantitative evaluation, but proof of convergence have been made. Thank you, and that's all for me.
Okay, thank you very much, Evan, for your presentation. Is there any questions for Kevin? Any questions? Okay, so we will move to the following presentation, which is about a biopsy module, localized cancer diagnosis as part of an integrated Cobra solution. And this will be, I believe, in the form of a video from Mr. Peter Werkstruck from Demcon Mechatronics in Delft, the Netherlands.
Hello, my name is Peter Wiskerke. I'm a project manager for the Demcon part on the Cobra project. Demcon is a large engineering company in the Netherlands, specialized in medical devices. And in the Cobra project, we are responsible for the biopsy module, which is used to take the biopsy from the prostate.
My name is Helene Kalkoen. I've been working as a system engineer on the development of the biopsy module by Demcon for the Cobra project. For this, we had to look into finding the right requirements to build an MRI-safe system, mainly oriented to selecting the right actuators and sensors, as well as material choice. Furthermore, we put a lot of effort in getting the accurate biopsy quality, so defining the speed we would need for firing the needle.
Hello, my name is Thomas Eisma, mechanical engineer at Demcon. Within the Cobra project, I was responsible for the mechanical design of the biopsy module. The main challenge was to design a fully functional model within the limited volume in the MRI scanner. As it will be used in an MRI scanner, we have used a limited volume of metals. and we looked mainly at plastics and ceramics.
Okay.
Yes, it was very short. We will have a view of the biopsy model during the demonstration that is starting right now. So now let me introduce Mario, which is a research engineer in the University of Lille, which will make the live demonstration of the integrated robotic solution.
Yeah. Hello, everyone. Can you hear me?
Yes.
Okay, so I'm Mario Sanz. I'm the engineer that works on the robot integration, and I'm going to show you a little bit how the whole thing works. Let me just switch to another another computer that now you should be able to see the whole setup. Yes. So let me show you a little bit how we set up this. We try to reproduce the whole setup that we use on the real conditions. This, of course, is a mock MRI. We wouldn't be able to put all those cameras and all those artifacts around it, computers, etc. Sorry, I'll go. So in here we've got, of course, our patient Bernard.
Mario, we are looking at your screen, which has our faces.
Sorry, can you hear me all right?
Yeah, we can hear you, but the screen you are sharing with us has our faces on.
Sorry, there must be. Okay, let's do this.
In my case, I can see the mock MRI and the robot.
Yes, I can also see the mock MRI and the robot.
Oh, sorry, maybe it's my screen. Sorry.
Sorry. Well, it's okay if nothing got lost so far. So we've got, as I said, patient, the Unilift. This is the solution that Noras provides us that allows us to keep the patient in place in the correct environment, and at the same time give us enough workspace for the robot to fit in. So the Unilift holds, maybe I should move a little bit Bernard's foot. We've got an MR compatible camera in here. So we clamped usually on the Unilift. This is our reference point for all the robot MRI registration. And this camera provided by MRC allows us to teleoperate and work on real time. We have the robot itself. Let me just take this away for a second. The first demonstration will be with the biopsy module, which is here, the video you saw before. The robot has 5 degrees of freedom that allows to perform this oblique insertion and minimize the number of entry points, as has been discussed before. We have a Phantom, which is our target for this biopsy, and I'll talk about it a little bit later. We have over here the seed loader device. So this is already loaded with some seeds, with a loader from Kurt Siegler. And we have over there, unfortunately, right now you can barely see it because it's hidden by the laptop, but there's the teleoperation panel. And we got another Phantom over here that I will show you interactively, sorry. So this one over here, and I'll talk a bit in depth about it. So we have also this, it's a rather target sandbox. It's another Phantom that we use in our tests to insert seeds. And yeah, I'm going to start by pushing the patient inside the MRI. Okay. Now everything's in place. You should be able to see. And I'm going to switch to the another. Oh, okay. So now you can see a whole bunch of cameras. So you get camera 1, which is the same global view that I've already shown you. You get camera 2, which is a close-up on how this works. We get camera 3 in the lower part, which has the teleoperation panel and the interface that is on the lower right corner. So it's labeled stream. So we're about to perform a little bit of navigation to illustrate a little bit the minimum entry point technique. And we're going to perform a biopsy live. So apologies for this delay. So Otman just arrived, is our operator. So he's going to perform live for you a small demonstration on how the teleoperation works. This you can see the whole stream screen, right? Yeah, it's visible. So
yes.
This is the interface that we use for real-time operation. So you can see on the right side of the stream screen, we got the live stream of the MR camera that allows us to target specifically what we're doing and try to register if we need manually. This is particularly beneficial for a biopsy when you don't know at first what is going on. So now the robot is starting to move. You can see the needle pulling back. We have also on the right side of the stream window a little 3D representation that also helps us to register or have a little insight of what is going on with respect to the target that we are looking for. This, of course, the intention is to replace it with live MRI images. Unfortunately, we don't have a live MRI, so we have to rely on synthetic data. The whole process, as has been explained by other partners, especially Kevin, focus on not being necessary to move the patient from the MRI. So this will allow to avoid this registration between MR images and biopsy. That is very helpful to find micro lesions and to overall accelerate and optimize the MR time. If yeah, don't forget, if you have any questions, you can interrupt me at any point. So now we're testing a little bit the motion. You can see in a close-up. We can try to move around an entry point. Otman wants to perform a biopsy. So this navigation panel allows us to test the accuracy of the robot real time, to get feedback real time, and also you can see it very small on the lower left part of the stream window. You can see how we can insert also predefined trajectories. So it's specialized for the treatment rather than biopsy. But if we got a detected lesion, we can also go for it, provided we get a good registration. So this is the biopsy module launching. And once we got the sample, we can pull it back and get the sample. You can go in here and just take out. I don't know if it's yeah, I'm not hiding. You can get in here and pull out the needle so that you can analyze furthermore. This is also a feature that was especially designed so that we can take in and out needles at will. Although given the possibilities that the MRI quality gives, the chances of performing multiple biopsies are very low, since we're looking into very specific spots, and we can drive it real time. This, of course, works all the time on a working MRI. This is very important. This is not MR compatible. It's MR operational. This we got samples, and we perform tests all the time on a real working MRI. So this is the actual configuration where the prostate of the patient, the mannequin in this case, is placed close to the isocenter, and the robot is usually even closer. Normally, it's placed rather underneath the unilift, so that it can get as close as possible to the patient, and it doesn't affect the quality of the images, even while dynamic acquisition. So maybe we can try to move around a single entry point. So so that you can see a little bit this oblique insertion principle. That is what allows us to minimize the number of entry points, try to avoid more complicated surgery. The penile bulb can be avoided. It's just a matter of the good trajectory. This gets further enhanced with the steerable needle, which is a module that is made to work together with the robot for the brachytherapy treatment. Now you can see how we move the robot around the endpoint, so the tip of the needle, and this is what allows us to perform multiple insertions or seed deposition with a single entry point. So maybe I'm going to leave you for a moment while we prepare the next demo, which would be the seed loader, in which we're going to perform a seed insertion. Maximilian,
Yes, thank you, Mario. So I will now share a short video about the steerable needle.
Hello, my name is Sean van der Dobbelsteen. I'm an associate professor at the Department of Biomechanical Engineering in Delft University of Technology.
And my name is Martijn de Vries and I'm a PhD researcher.
Within our department, we mainly focus on the development of novel medical instruments for minimally invasive therapies.
And within my research, I'm focusing on the development of a novel steerable needle design to optimize LDR brachytherapy interventions. Here the conventional LDR procedure is shown. The prostate in green and important structures around it are visualized. The needle template and transrectal ultrasound probe are positioned and 15 to 25 straight needles are placed in the prostate, leaving behind permanent seeds. However, some areas of the prostate cannot be reached because they are occluded by the urethra or the pubic arch. This may cause suboptimal dose distribution. Next to this, with straight needles, trajectory control may be lacking and sensitive tissues cannot be avoided. The designed steerable needle should allow for 1. Better control of the needle track and end location during needle placement, and 2. Allow for an enlarged reach within the prostate for a more homogeneous dose distribution. In Delft, we manufactured a compliant steerable needle comprising of an outer catheter and a steerable inner needle. Here you can see the design of the inner needle. The needle rod is effectively split into 4 quarters. The steerable needle can be actively steered in all directions during an insertion to allow for better control of the needle trajectory. The outer catheter will be left behind in the body, functioning as a channel for radioactive seed placement.
So this is it for the presentation of the steerable needle technology. So Martin de Vries is present. So if you have some question on this model, do not hesitate to ask. He will be happy to answer.
So thank you, Maximilian. We're ready for the next demonstration. Maybe I can share a screen. You can all see it. Okay, so we're back. It's pretty much the same configuration. The only thing we changed is the needle on camera 2. You can see the close-up, the needle and the target. And also we switched the teleoperation panel view to the seed loader view. This will perform a full seed load up to the target, and we will hopefully be able to see something at the end. and the rest is just the same global view and the stream view of yeah. So how this works, it's we got two parts: the loader that will push seed up to the exit point of I think we're to the exit point of the automatic loader device, and the feeder that will go all the way through this catheter up to the needle, and then to the target. So if you're ready, we can start. Yeah. So okay. So now here is the seed is being pushed. Once it reaches this sensor, this mandrel is pulled back. And now we start to feed. It's a very thin detail. And you should be able, no, you won't be able to see where this is going. I'm going to show you with my finger because now we're going this way. Yeah, now it's in the needle. And the seed seems to have been deposited. The guide wire is pulling back. This is a particular guide wire provided by Marvis, which is MR compatible and allows us to perform this very technical gesture. Doesn't look like, but we have a big problem with friction, and this guide wire with the whole solution allows us to perform this automatic seat load. You can see that there is a little bit of slack in the catheter. This allows us to move, get some play on the positioning of the seed loader. And I'm going to show you, sorry, that's it. There you go. So, I don't know if where you will be able to see it. Maybe on this camera, it's a bit close. So I don't know if you can see something.
Yes, we can see on the top right camera. Yeah.
Yes. So this is the seed placed in this phantom. Just for this little detail, the phantom of the target sandbox that we use is made with silicon gel, which is not the best material for MR visibility, but is the best given the properties that we need. So this is for the seed loader device. And I'm going to talk about another thing, which is the last thing I'm going to show. It's the bio-inspired phantom. So this is a particularly useful tool that has been developed for this application in the Cobra project. So the main goal here is to
Louis, are you sharing the screen?
Wait a second. It's let me stop a little bit. Okay, so I'm going to place things so that you can see it. So yeah,
Is it me only? I cannot see.
No, I can't see anything either.
So, okay, we are ready. We're back. I'm going to.
Mario, we don't see your screen. Your feed.
Not
it's
yet.
Blank. Okay.
Now you should be able to see it.
Good. Yes. Thank you.
Okay. Well. Thanks. So this is the last part of the project, which we wanted to talk a little bit about all this technology that you've been seeing. There is one big question that raises up: is how to deploy all this in terms of teaching the clinicians on that, and that is where this phantom comes in place. So this is a very particular phantom because it's active, it's mobile, and we can use a simulation to couple it on so that we can. It's of course MR compatible like all the other elements on this project, but this one can also work on as a standalone. It's some sort of soft robot or kind of an interface. Let me just start up a little thing here. So this will help practitioners to get trained. With the overall pipeline that we've presented here, one of the main problems that comes across is how to handle this prostate motion that is new, since we don't have an ultrasound probe and we don't have any sort of pin to hold the prostate in place. We need to see what is going on, and that is what this tool helps us to. Okay, now it's working. Okay, so this is an interface, a soft robot, in which you can have the motion of the phantom. There is these 4 tubings that go along each of these arms that holds it in place, and yes. So the streaming capabilities give some lag. But actually, when I move it around, the simulation moves with it and allows that. Maybe it's inverted on your view. No, it's not inverted in your view. It allows us to reproduce the motion of this phantom and its deformation, just with the value changes of these pressure points, these cavities that are inside those attach points. Those are arbitrarily placed, so we concentrate all the efforts in those 4 points. Obviously, when you know a little bit about the anatomy, you know that ligaments are not placed in the same spot. But our pipeline goes beyond that. We can place it arbitrarily or even generate the phantom with patient-specific data. That is a particularly useful tool, first for training the doctors on this new technique, and also to treat some particularly problematic cases in which the shape or the position of the targets are a problem. We can integrate everything in a simulator so that we can train and even evaluate. This simulator, which is the SOFA framework, has already been used for medical simulation, and some applications for practical training are also in place. And there is one last feature that I wanted to show. Maybe you notice this cavity in the center. It's placed where the urethra should be, and it's attached to a syringe that I have in my hand. So when I pump some air, this is very difficult to see because the inflation is not so obvious, but the cavity inflates, and the prostate with it. This is made to emulate swelling. So during the intervention, obviously, targets will migrate due to the motion of the prostate itself, but also to the swelling. As we puncture it, it starts to swell. It's obviously not anatomically correct, because swelling happens at the spot where the lesions occur, but it's a very useful tool for us to evaluate how targets migrate, how we can adapt the trajectories on the robot, and this adaptive characteristic of the pipeline within the SOFA, within the Cobra project, is the best scenario for future interventions. We're already looking into other organs that, for example, are affected by respiration, the breathing of the patient, more than the prostate. The lower abdomen is not so sensitive, but we get these kind of features that you're seeing in where targets can migrate. And of course, this is we try to perform the most difficult kind of effect to simulate, but there is other interactions with the environment, such as bladder inflating, or well, filling, not inflating, and other kind of bowel movements, or whatever interacts with the prostate itself, which is an external parameter that we cannot take into account prior to the intervention, and that greatly affects this registration when we use hybrid systems, hybrid techniques, such as taking a MRI and then afterwards going to biopsy. This can be taken into account on real time for the patient and for the doctor to train. And this is one a very important part of the project, because it's our evaluation target. So if maybe I didn't go too much into the details of how it works, if you got any questions, I'm open to answer it.
Any questions? So Mario, when you were touching the Phantom,
yes,
software was adaptive to your touch, and we can see actually on the other screen the arrows going up and down, the arrows on the. So
yes,
this is automatic. Nobody was doing that. This was the software.
Yeah. This is actually those arrows that you can see are the estimation that the framework gives of the applied force. That I didn't mention it, but that is also another feature that is very useful. The multiphysics nature of SOFA is what allows us to mix all the physical effects that we can handle. The framework handles, in this case, pneumatics, but also any other kind of mechanical drives. For example, we can simulate hydraulics, like some sort of, for example, what I mentioned earlier, the bladder filling with the weight of the liquid in it, or we can even have some sort of I've seen electrophysiology simulation with SOFA, and the same kind of physical phenomenon applies to, for example, cryoablation or even radio ablation. So the same kind of simulator can be used for more complex scenarios.
Thank you very much. Thank you very much.
Welcome.
I mean, it's excellent, really, that you managed to show us the 4 simultaneous cameras at the same time to different features. I think for me, at least, this is even better than if we were actually seeing it in real time, because every one of us, if it's in physical situation, will be concentrating on part of the room. But using this facility now, we can see all 4 cameras simultaneously, which I think is works even better for in terms of visualization of how things are going on at the same time. So well done, really, for integrating all of this views for us, and also in engineering it in this way. So well done. Thank you very much. Any questions from the audience to Mario? Yeah, and his team. Okay. So I think this was really the highlight of the day, is to show the demonstration of the robot and the phantoms, and how we integrate all of this together with this advanced technology. And also what Mario touched on, which is the training aspects, which I think this is our next major challenge, is how to train clinicians to use such technologies. So I think we have time for questions. If we have any questions from the audience or any comments about future plans, I just want to remind you that we have on the final meeting is going to be in University of Lille. Anybody would like to from the UK to travel there, from the people who are from outside Cobra, you are most welcome to join us. This would be the final demonstration on the 24th of June in Lille, in the north of France. Rujdi, do you want to add anything?
Yes, thank you, Ashraf. Yes, thank you for the organization and sharing this workshop. It was supposed to be in presence or face to face. Unfortunately, due to the actual conditions, for traveling, etc. We did it here. So I thank the auditors and the followers for this workshop. Our interest from this project is to reach our main target, which are practitioners, urologists, radiation therapeutists, physicists, working on the field of local or minimal interventions under MRI guidance. And the aim here is to perform solution that can go to the market at the end of the project. Our interest, that means by after the project, to see how we can also increase the level of the maturity of the project or the concept to be fastly integrated in the market. It's for that. During this end phase, we want to start the on-life tests on animals, specifically for the biopsies in real conditions, which hope that the results will help us to go for the next step, let's say certifications, and and the advantage of having a collaborative partnerships of Cobra is to be able to have at the end a solution that can satisfy our group target, from different centers and hospitals in Europe generally. And while we know that from one region to another, from one hospital to another, even we have even the strategy of the intervention here for biopsy and brachytherapy is globally similar, but the practice is relatively different. So our idea here from this project that we collect the maximum of constraints and practice from different target group, and we tried to answer almost of them through this this advanced prototype. This is what I can conclude from this workshop. Thank you, Ashraf. Thank you, all of you, for managing this. And you have a nice picture behind you. Yes.
Thank you.
Hi, can I ask also a question?
Yes, of course. Yes.
Yeah, my name is Ben Van Este. I'm a radiation oncologist. I'm a clinician and also a brachytherapist. I work in Ghent University now in Belgium, and I previously worked also in Mastro Clinic, where I'm also consultant brachytherapy. But I just met the project at the last Astro, and so that was the reason why I was invited. I'm really excited about all the preclinical work that you did now. I just followed a few presentations and also the nice video. But and so additional with your final clinical goal, I'm very eager and also interesting to participate on that.
All right.
But I've got one remark or question, because now it's completely set up as a very fancy clinical tool, so that it's completely MR guided, and in practice, so in traditional clinics, that is, I would say, only preserved for the happy few, with an MR installed and to put all the MR guidance on that. Is there also, or are there also some thoughts to use it on an ultrasound base or on an ultrasound guidance with additional MR or PSMA or additional imaging fusion models on that, so that it could be easily, broadly implemented?
Yes. To answer you to this question, our story in terms of mini-invasive brachytherapy under image guidance started initially with ultrasound. We did previously in 2016 a solution with the collaborative robot under the guidance of the ultrasound. One of the limitation of such technology where we progressed to the MRI, I explain you the advantage. The first was under ultrasound. One of the limitation is not from the robotic side. The robot is accurate when the target is well known. Okay, knowing that the biological target that we want to track is soft, and due to the interaction with the needle, it can move. Due to multiple interaction with the needle, it can make an inflammation, or it can change in terms of positioning. So even if for the prostate is a relative displacement, but when we implement a full robot automated solution, we need more accuracy than what it exists nowadays from conventional practice. So to converge to the limitation is how we can adaptively track the target, the biological target during the intervention using a robotized system. With the only ultrasound solutions, we couldn't do this, but because it's not easy to track first micro lesions with ultrasounds to detect them first and then track them in real time. We did we test multiple algorithms here to the positions of the target during the insertion, but it was not possible. It's for that we shift to the MRI. So the MRI technology is helpful for detection of micro lesions. This is one objective. And secondly, it is helpful for tracking the motion of the microbiological organ or the micro lesions during the intervention. However, the MRI environment is very costly. All right. If we integrate solution like this, we have to attract, that means the end users, we have to justify that we optimize the time of the intervention. For that, what we did, we worked actual conventional brachytherapy or biopsy can be practiced by making a multiple insertion of needles. Okay. One of our solution for the issue of optimizing the time of intervention under MR is to minimize the number of insertions through the perineal side. That means we try to cover multiple lesion targets inside the prostate to optimize, to have a constraint of access point through the perineal side. Instead of having a multiple point access, we minimize. That means from 1 to 2 point access from the perineal side, the robot can reach multiple targets inside. In this case, what it means, we can reach different position inside the prostate with only by using only 1 or 2 maximum needles, not a multi-disc. Why? Because if you are expert here. If we remove the needle from the body, we have to change it, and changing the needle can cost, in our case, 5 minutes for changing and 5 to 10 minutes for calibration of the robot again. So to optimize this, we use only 1. Our objective through this prototype, that means preparation of the patient plus the robot calibration and the needle and the intervention will take less than 40 minutes. In this case, of course, such intervention can satisfy, because at the hospital, if you want to plan a scenario of diagnosis with the MR, okay, finding a slot of 40 minutes between 2 scans can be possible. Yeah, this is our objective. That means the intervention takes 30 minutes, while 10 minutes of preparation globally. This is our main objective. Now, to answer also, to have from transferability point of view, to answer also about your question, this prototype is MR 3 Tesla compatible. What it means, compatibility not means that all the components are non-magnetic that can operate in such environment, but operated inside, which is make a difference. Because actually, if you see in the literature, what it exists as a technology with MR compatible minimally invasive robot is something that we have a scan. We put the patient inside the MR, we scan it in different, specifically in position that we can do another scan with the ultrasound, etc. So we scan them first, we remove it from the MR, we put it in the other room, annex room, we match the MRI with the ultrasound, we use the ultrasound for the intervention, we do the intervention, and we can replace the patient inside to check if, but here it's not, let's say, optimized scenario process globally in terms of accuracy, because even if I am guided by the ultrasound images, but are matched with a static MRI image. That means in terms of accuracy, matching and placement is not easy to justify it. All right, then replace it. Here we can block the MR for 2 or 3 hours for all these steps. So our idea is to integrate everything and to optimize the time of the intervention and solution. Of course, the daily practice nowadays for the brachytherapy is not to make to do the brachytherapy with 1 or 2 needles, but here we can adapt also the treatment planning for the making deposit in oblique ways. Yes, in oblique ways, and this can have an impact for the future development, and this can be possible by collaborating with you and other experts in this field. So globally here is now, if you want that we can use this robot with only ultrasound, this is possible also. Okay, but it can be easy to use it for biopsies, for example, because even if it's compatible with 3 Tesla MR, it's compatible for scan, CT, for it's not the problem itself. So this is yeah.
Okay, but no, that's yeah. Thank you very much. But so it's indeed, I agree completely. Your MR is much better, and to make visible the micro lesions, to track, etc. But I was thinking like a real clinician, and I know like only in the big cancer centers they got like the approach to get an MR in the OR or the combination of it. But like when you go to smaller centers and to get a more easily implement or to obtain the biggest implementation, it should be also, in my opinion, then combined with ultrasound. So, but it's very good to hear that you can do it. There are also a lot of fusion programs now that you can make your MR fused on your ultrasound. So yeah, that would be I think of much of interest to do it in a continuation.
I exchanged during the ISRO event with the BK for the ultrasound that they said they are interested to see how we can combine, we can match with because they developed the tools matching MR images with the ultrasounds, and they are really interested to see how this can help the integration of such a robot.
I think, and to optimize it optimize it. But so yeah, it's very nice program. So I was happy and to follow this now, because I didn't knew it before.
Yes.
So
we are happy to exchange with
for
you.
your work already.
All right, thank you so much. Even if Ghent is not far from Lille, you are welcome.
No, it isn't. No, it isn't. I was checking to follow it live then.
Okay, you are welcome. Thank you so much.
Thank you.
Okay, thank you very much, Rushdie, and thank you for the question. Is there any other question? I think the key from what Rushdie mentioned, the key word really is the what we are trying to do is to have the adaptation, the adaptive environment, and I think this is really the way forward. That how do we adapt to the changing situation, whether and to feedback to the algorithm, and the other challenge obviously is the training aspect. Is there any other questions or any other comments before we finish the? I would like to thank everybody involved. Thank you very much for all the speakers. In particular, thank you very much to Mario and the demonstration, which really made us as if exactly even better than in terms of visualizing the whole system, how it works. It was an excellent demonstration.
Thank you, Mario. Thank you, the team.
Thank you very much.
Thank you, everyone.
Thank you. Thank you very much. Yeah, so with this, I will close the meeting now, and
thank you.
Thank you very much. Thank you.
Thank you, and congrats for the team.
Thank you.